On November 14, 2023, something terrifying happened. Voyager 1, the spacecraft that had been humanity's ambassador to the stars for nearly half a century, suddenly went silent. Instead of sending back the usual stream of scientific data, it began transmitting nothing but meaningless gibberish, an endless stream of binary ones and zeros that made absolutely no sense. The spacecraft, now more than 15 billion miles from Earth, seemed lost forever in the dark void of interstellar space. Scientists at NASA's Jet Propulsion Laboratory stared at their screens in disbelief. This wasn't supposed to happen. Not to Voyager, not to humanity's farthest-reaching messenger to the cosmos. If you like the content, leave a like and subscribe to the channel, as tonight we look into why Voyager's signals suddenly made no sense and what secrets it was hiding. Get ready as we begin. The diagnosis was grim. A critical memory failure had occurred in the spacecraft's flight data system, the very brain that controlled its operations. After nearly 47 years of flawless service, after surviving the radiation belts of Jupiter, the rings of Saturn, and the crossing into interstellar space itself, Voyager 1 was dying. The engineers faced an impossible decision. They could let it go, allow this magnificent machine to drift silently into the void, or they could attempt something that had never been done before. They would have to perform emergency surgery on a computer system designed in the early 1970s, using technology older than most of the engineers themselves, across a distance so vast that radio signals travelling at the speed of light took 22.5 hours to reach the spacecraft. The team made their choice. On April 18, 2024, they began the most delicate and dangerous operation in the history of space exploration. They would reallocate the corrupted code to other areas of the probe's memory, essentially rewiring the brain of a spacecraft that was farther from Earth than any human-made object had ever been. Every command they sent was a leap of faith into the unknown. They would send a signal, then wait 45 hours for a response. 22.5 hours for the signal to crawl across the solar system and beyond, and another 22.5 hours for Voyager's reply to make the same impossible journey back. It was like performing brain surgery on a patient in slow motion, where every decision took 2 full days to see the results. 2 days after that first attempt, on April 20th, something miraculous happened. A signal came back. Not the meaningless noise that had been haunting mission control for 5 months, but real data. Clear, coherent, beautiful data. Voyager 1 was alive. The engineers erupted in celebration, some with tears streaming down their faces. They had done it. They had brought back humanity's most distant explorer from the edge of oblivion. But this dramatic rescue was just the latest chapter in a story that began nearly 5 decades ago. A story of 2 small spacecraft that would rewrite our understanding of the solar system and venture into a realm where no human creation had ever gone before. The story of the Voyagers begins with a cosmic alignment that happens only once in a human lifetime. In the late 1970s, the planets of our solar system arranged themselves in a configuration that occurs only once every 175 years. Jupiter, Saturn, Uranus, and Neptune lined up on one side of the Sun, creating a unique opportunity that NASA scientists realized they couldn't pass up. This planetary alignment meant that a single spacecraft could visit all 4 gas giants using a technique called gravitational assist, where each planet's gravity would act like a slingshot, hurling the probe toward the next destination without requiring additional fuel. It was an opportunity that wouldn't come again for nearly 2 centuries. NASA seized this rare chance and approved what would become one of the most ambitious missions in space exploration history. Originally called Mariner Jupiter-Saturn, The project was renamed Voyager because these new probes had progressed so far beyond the Mariner spacecraft family that they deserved their own identity. 2 identical spacecraft would be built, each equipped with cameras, sensors, and instruments to study the giant planets and their moons. But here's where the story gets interesting. The mission was designed with a brilliant backup plan built into its very foundation. If everything went perfectly, one probe could continue beyond Saturn to visit Uranus and Neptune. If something went wrong, well, at least they'd have data from Jupiter and Saturn. On August 20th, 1977, Voyager 2 lifted off from Cape Canaveral, riding a pillar of fire into the Florida sky. 2 weeks later, on September 5th, Voyager 1 followed its twin into space. Now you might be wondering why Voyager 1 launched second but has the number 1 designation. The answer lies in their trajectories. Even though Voyager 2 left Earth first, Voyager 1 was placed on a faster, more direct route to Jupiter. It would overtake its twin and arrive at the giant planet first, travelling at a blistering 38,000 miles per hour compared to Voyager 2's 34,000 miles per hour. Just 13 days after launch, Voyager 1 accomplished something that gave humanity a new perspective on our place in the cosmos. From 7.2 million miles away, it captured the first photograph showing both Earth and the Moon together in a single frame. That image became a symbol of the grand journey that lay ahead. But to truly appreciate what these spacecrafts would accomplish, we need to understand just how remarkable they were as machines. Remember, these probes were designed and built in the early 1970s, an era when pocket calculators were cutting-edge technology and personal computers didn't exist. The computer systems aboard each Voyager spacecraft had a combined memory of just 69 kilobytes. That's right, kilobytes. Not megabytes, not gigabytes, but 69 kilobytes total. To put that in perspective, that's barely enough memory to store a single low-resolution photograph on your smartphone. The average text message you send today uses more memory than the Voyagers had to work with for their entire mission. Yet these primitive computers, by modern standards, would go on to execute one of the most complex and successful missions in space exploration history. The data from the spacecraft's instruments was recorded on 8 track tape machines, though not the kind you might remember from old cars. These were specially designed digital tape recorders manufactured by Odetics Corporation, capable of recording data at different speeds depending on the situation. The magnetic tape itself was treated with a secret process to prevent it from degrading in the harsh environment of space, where temperatures swing from extreme heat to extreme cold, and radiation bombards every surface. Whatever those manufacturing secrets were, they worked incredibly well, because decades later, these tape machines are still functioning perfectly. The spacecraft computers could execute about 81,000 instructions per second. Your smartphone is roughly 75,000 times faster than that. The data transmission rate back to Earth was a painfully slow 160 bits per second. If you tried to stream a movie from Netflix over a Voyager connection, it would take about 8.5 years to download. Powering each spacecraft were 3 radioisotope thermoelectric generators, devices that convert heat from decaying plutonium into electricity. These RTGs were mounted at the end of a long boom to keep their radiation away from the sensitive instruments. When the Voyagers launched, these generators produced about 470 watts of power. Today, nearly 5 decades later, they're still producing electricity, though the output has gradually decreased as the plutonium slowly decays. This declining power supply is the ticking clock that will eventually silence the Voyagers forever. But we'll get to that heart-wrenching reality later. Each spacecraft was equipped with 11 different scientific instruments, including cameras, spectrometers, magnetometers, and plasma detectors. But perhaps the most fascinating cargo aboard each Voyager was something that had nothing to do with science. Attached to each spacecraft is a golden phonograph record, a time capsule designed to tell any alien civilization that might one day find these probes about the beings who built them. These golden records, created under the direction of a committee led by the famous astronomer Carl Sagan, contain 115 analog encoded photographs, greetings in 55 different languages, a 12-minute montage of sounds from Earth, and 90 minutes of music ranging from Bach to Chuck Berry. The records are housed in protective aluminum jackets, along with instructions showing how to play them and diagrams indicating where Earth is located in the galaxy. It's a message in a bottle cast into the cosmic ocean, a greeting from a species that dares to imagine it might not be alone in the universe. In 1979, both Voyagers reached Jupiter, and what they discovered there would change our understanding of the solar system forever. The giant planet revealed secrets that had been hidden for billions of years. The spacecraft discovered that Jupiter had faint rings, something that had never been detected from Earth. They found 3 previously unknown moons orbiting the giant planet. They captured detailed images of Jupiter's 4 largest moons, the Galilean satellites, and confirmed that Ganymede is actually the largest moon in the solar system, bigger than the planet Mercury and larger than Titan, which had previously held that distinction. The images of Europa revealed a surface covered in smooth ice, crisscrossed with mysterious cracks and ridges. This data gave birth to one of the most exciting hypotheses in planetary science, that beneath Europa's frozen crust might lie a vast ocean of liquid water, potentially harboring alien life. But the most dramatic discovery came from Io, Jupiter's innermost large moon. Voyager 1's cameras captured something that stunned scientists around the world. A volcano was erupting on Io's surface, spewing material hundreds of miles into space. It was the first time in human history that an active volcano had been observed anywhere beyond Earth. Further observations revealed that Io is the most volcanically active body in the entire solar system, its surface constantly being reshaped by hundreds of active volcanoes. The spacecraft also got their first close-up look at Jupiter's Great Red Spot, a storm that has been raging for at least 400 years, possibly much longer. The spot is so large that 3 Earths could fit inside it. The detailed images and data from the Voyagers showed that this storm is essentially a high-pressure system in Jupiter's atmosphere, rotating counterclockwise at wind speeds of up to 270 miles per hour. Using Jupiter's immense gravity as a slingshot, both Voyagers then headed towards Saturn, arriving in 1980 and 1981. This encounter would mark a crucial turning point in the Voyager mission. The original plan had been to study Jupiter and Saturn over a 4-year mission, then call it complete. But NASA had cleverly designed the trajectories to allow for something more ambitious. The key decision revolved around Saturn's largest moon, Titan. This moon is unique in the solar system because it's the only moon with a dense atmosphere, thicker than Earth's atmosphere in fact. Scientists desperately wanted a close look at Titan, but there was a catch. The trajectory needed to get a good view of Titan would bend Voyager 1's path in such a way that continuing onward to Uranus and Neptune would be impossible. NASA had to make a choice. Send Voyager 1 close to Titan and sacrifice any chance of visiting the outer planets, or skip the close Titan encounter and continue to Uranus and Neptune. In the end, they decided to have it both ways. Voyager 1 would be directed toward Titan for a close flyby, giving scientists their best look yet at this mysterious moon. Meanwhile, Voyager 2 would take a different path, one that would allow it to continue the grand tour to Uranus and Neptune. It was a decision that would lead to both triumph and disappointment. The probe sent back stunning images of Saturn and its magnificent rings, revealing details that had never been seen before. The rings, it turned out, were far more complex than anyone had imagined, consisting of hundreds of narrow bands with intricate structures and patterns. The spacecraft discovered 4 new moons orbiting Saturn. One moon in particular captured everyone's imagination. Mimas, a relatively small moon, turned out to have a truly distinctive feature. A massive impact crater called Herschel dominates one side of the moon, giving it an uncanny resemblance to the Death Star from Star Wars. The crater is so large relative to the moon's size that the impact that created it probably came close to shattering Mimas completely. But then came the disappointment with Titan. When Voyager 1 made its close approach, the cameras revealed nothing but a featureless orange haze. Titan's thick atmosphere, rich in nitrogen and methane, was completely opaque to visible light. The surface remained hidden, its secrets locked away beneath the impenetrable clouds. Scientists would have to wait another 24 years until the Cassini-Huygens mission arrived at Saturn to finally see what lay beneath Titan's atmospheric veil. The data did reveal something fascinating, though. Titan's surface temperature was right around the triple point of methane, a unique condition where methane can exist as a solid, liquid, and gas, much like water does on Earth. After Saturn, the paths of the 2 Voyagers diverged forever. Saturn's gravity had accelerated Voyager 1 significantly, altering its trajectory and making it the fastest spacecraft ever built by humanity. But this speed boost came at a cost. Voyager 1 was now on a path that would take it out of the plane of the solar system. Its mission to visit other planets was over. Voyager 2, meanwhile, continued the grand tour alone, heading for Uranus. The journey to Uranus took 5 years, and on January 24, 1986, Voyager 2 made its closest approach, coming within 50,600 miles of the ice giant's cloud tops. What it found there challenged everything scientists thought they knew about planetary composition. Uranus turned out to be dramatically different from Jupiter and Saturn. While those gas giants are composed primarily of hydrogen and helium, about 90% by mass, Uranus contains these light elements only in its atmosphere. Beneath the atmospheric layer lies an ocean of water, ammonia, methane, and hydrogen sulfide, surrounding a core of rock and ice at the planet's center. This discovery led to the creation of a new planetary classification. Uranus and Neptune were designated as ice giants, distinct from the gas giants Jupiter and Saturn. Voyager 2 also discovered that Uranus is the coldest planet in the solar system, with temperatures dropping as low as -371 degrees Fahrenheit, even colder than Neptune, which is farther from the Sun. This seems counterintuitive at first, but it's because Uranus has very little internal heat compared to the other giant planets. Most of its warmth comes from the Sun, and at that distance there isn't much warmth to be had. After collecting data on Uranus and its moons and rings, Voyager 2 pressed on to its final planetary target, Neptune. The journey took another 3.5 years. On August 25, 1989, Voyager 2 made its closest approach to Neptune, and to this day, it remains the only spacecraft that has ever visited the solar system's 8th and most distant planet. The images Voyager 2 sent back revealed Neptune as a vivid blue world, though later analysis of the data showed that its true colour is actually closer to a blue-green or teal. The spacecraft discovered that Neptune has the fastest winds in the solar system, with some storm systems showing wind speeds of up to 1,200 miles per hour. Voyager 2 also got a close look at Neptune's largest moon, Triton, and what it found there was absolutely bizarre. Triton is one of the coldest objects in the solar system, with surface temperatures around -391 degrees Fahrenheit. Yet despite these frigid conditions, Voyager 2's cameras captured evidence of active geysers erupting from the surface, shooting nitrogen ice and gas miles into the thin atmosphere. While Voyager 2 was exploring Uranus and Neptune, completing the grand tour of the outer planets, Voyager 1 could only metaphorically watch with envy. After its encounter with Saturn, mission controllers had shut down many of Voyager 1's instruments to conserve power, leaving only the tools needed to study the space environment itself. But Voyager 1 would soon have its own moment of immortality. On February 14, 1990, from a distance of 3.7 billion miles from Earth, Voyager 1 turned its cameras back toward the inner solar system one last time. In the resulting image, Earth appears as a tiny speck, barely visible, just a pale blue dot measuring 0.12 pixels in size, suspended in a sunbeam. This photograph, known as the pale blue dot, became one of the most iconic images in the history of space exploration. It inspired Carl Sagan to write his famous reflection on the image, reminding us that everyone we've ever known, every human civilization that has ever existed, lived on that tiny mote of dust suspended in a sunbeam. After this final photographic session, the cameras on both Voyagers were permanently shut down. There was no longer any need for them, and the power they consumed could be better used by other instruments. The spacecraft entered a long period of relative quiet, cruising through the outer reaches of the solar system. For a decade and a half, they journeyed on, sending back data about the environment at the edge of the sun's influence, but making no headlines. Then, on August 25, 2012, something extraordinary happened. Voyager 1's instruments detected a sudden and dramatic change in its environment. The number of charged particles emanating from the sun, particles carried by the solar wind, dropped sharply. At the same time, the count of galactic cosmic rays, high-energy particles that originate from outside the solar system, began to rise. The implications were staggering. Voyager 1 had crossed the heliopause, the boundary where the sun's influence ends and interstellar space begins. It had become the first human-made object to leave the solar system and enter the space between the stars. 6 years later, on November 5, 2018, the slower-moving Voyager 2 crossed the same boundary, becoming the second spacecraft to enter interstellar space. Both spacecraft were now in a realm where no human creation had ever ventured, and what they discovered there would challenge and overturn long-held scientific assumptions about the boundary of our solar system. To understand the significance of these discoveries, we need to understand what the heliopause actually is. Our sun constantly emits a stream of charged particles, primarily protons and electrons, that we call the solar wind. This wind flows outward in all directions, creating a bubble around the sun and its planets. This bubble, called the heliosphere, extends about 11 billion miles from the sun. Within this bubble, the solar wind dominates the space environment, deflecting and moderating the galactic cosmic rays that would otherwise flood the inner solar system. The heliopause is the boundary where the pressure of the solar wind pushing outward is balanced by the pressure of the interstellar medium pushing inward. Scientists had long theorized about what would happen at this boundary, but until the Voyagers arrived there, it was all speculation. The traditional theory held that the solar wind would gradually weaken as it moved farther from the sun, eventually fading away into interstellar space in a smooth transition. But the Voyager data told a completely different story. The solar wind doesn't gradually fade. Instead, it reaches a sharp boundary where it essentially stops dead. The transition from the heliosphere to interstellar space happens over a relatively short distance, creating a distinct border between the two environments. This discovery fundamentally changed our understanding of how the solar system interacts with the galaxy around it. The data revealed something even more surprising about the shape of this boundary. On the side facing the direction of the Sun's motion through the galaxy, the heliosphere is roughly spherical, but on the trailing side, it stretches out into a long tail, like a comet. This tail extends for billions of miles behind the Sun as it moves through the galaxy. Even more intriguing, the heliopause itself is not a smooth, static boundary. It's constantly moving and changing, distorted by massive waves that appear at unexpected, non-uniform angles. These waves can be enormous, reaching heights of 10 astronomical units. That's 10 times the distance between Earth and the Sun, or about 930 million miles. The discovery of these waves was completely unexpected. Scientists had no theoretical framework to explain them. Even more puzzling, the Voyager data showed that the heliopause underwent rapid, dramatic changes over very short periods. This might explain why there was such a large time gap between when Voyager 1 and Voyager 2 crossed into interstellar space. 6 full years separated their crossings, despite the fact that Voyager 2 was only a few years behind Voyager 1 in the journey. The data also revealed mysteries about the temperature and density of the solar wind near the heliopause. Astrophysicists had predicted that as the solar wind particles slowed down due to interaction with interstellar matter, they would compress, causing a sharp increase in both temperature and density. And while such an increase was indeed observed, the measured values were only about 1/10 of what the theories predicted. Where did the missing energy go? No one knows. This discrepancy suggests that there are physical processes occurring at the boundary of the solar system that we don't yet understand. The Voyagers also discovered fundamental differences between the heliosphere and interstellar space. The interstellar medium consists of denser, colder plasma compared to the hotter, less dense plasma near the solar system's boundary. These two types of plasma don't simply exist side by side. They interact with each other, mixing and creating a sort of boundary layer between the heliosphere and interstellar space. The implications extend beyond our solar system. The interactions between stellar wind and the interstellar medium aren't unique to the Sun. Every star in the galaxy exists within its own version of the heliosphere, and the processes the Voyagers are observing at our heliopause likely occur around every other star as well. This means that understanding our own solar system's boundary helps us understand the behavior of stars throughout the galaxy. The Voyagers also measured the strength of the interstellar magnetic field and found that it's 2 to 3 times more powerful than previous estimates suggested. This has significant implications for our understanding of how cosmic rays propagate through the galaxy and how stellar systems are affected by their galactic environment. The stronger magnetic field means that interstellar particles exert about 10 times more pressure on the heliosphere than scientists had expected. Perhaps most intriguing of all was a discovery Voyager 1 made in recent years. The spacecraft detected a continuous hum in interstellar space, a signal that has remained remarkably steady. The hum consists of plasma waves oscillating at a frequency of about 3 kHz, and it has persisted almost unchanged for nearly 3 years. This is the most stable and long-lasting signal of its kind ever detected in interstellar space. When scientists converted these electromagnetic waves into sound waves that human ears can perceive, they created an audio recording of what interstellar space sounds like. It's an eerie, otherworldly tone, a voice from the void between the stars. Most scientists believe this hum is generated by plasma waves traveling through the interstellar medium. Plasma is a state of matter consisting of charged particles, and it's the primary component of the material between stars. What makes this particular signal so fascinating is its remarkable consistency. Even after Voyager 1 travelled another billion miles through interstellar space, the hum remained essentially unchanged. This unprecedented stability has led some scientists to speculate that there might be some unknown source of energy in the local interstellar medium that's generating or sustaining this hum. But that's just speculation at this point. The truth is, we're still in the very early stages of understanding what interstellar space is really like. Throughout their journey through interstellar space, both Voyagers have continued to experience technical challenges. In 2012, while 14.6 billion miles from Earth, Voyager 1 began transmitting chaotic data about its position. Instead of normal telemetry, it sent sequences of zeros or the number 377 repeated over and over. This mysterious signal puzzled scientists. Was it trying to tell them something important? Was it a malfunction? After extensive analysis, they determined it was indeed a malfunction, related to the spacecraft's attitude control and maneuvering system. Although they could still control the spacecraft, Voyager 1 had lost precise awareness of its own orientation in space. The problem was likely caused by cosmic radiation damaging the navigation computer. NASA engineers successfully resolved the issue by rerouting the telemetry through a different onboard computer. Then came the crisis of November 2023, the memory failure that we discussed at the beginning of this story. For 5 agonizing months, Voyager 1 remained silent, transmitting only meaningless data. The repair process was a testament to human ingenuity and determination. The engineers had to identify which specific chip in the flight data system had failed, figure out how to move the corrupted code to undamaged memory locations, modify that code to work in its new location, and do all of this without being able to test anything beforehand. Every command they sent was essentially a shot in the dark, and they had to wait 45 hours to see if it worked. The fact that they succeeded, that they managed to resurrect a spacecraft using technology from the 1970s across a distance of billions of miles, stands as one of the greatest achievements in the history of space operations. But these malfunctions are grim reminders that time is running out for the Voyagers. The radioisotope generators that power both spacecraft are slowly decaying, producing less electricity with each passing year. NASA estimates that the critical instruments will be able to function until around 2025, just months away now. After that, mission controllers will have to begin shutting down instruments one by one to conserve power. Each shutdown will reduce the amount of data the Voyagers can collect and transmit. By the early 2030s, around the 50th anniversary of their launch, both spacecraft will likely no longer have enough power to communicate with Earth. That will mark the end of the mission, the moment when humanity loses contact with its farthest ambassadors to the cosmos. After that final goodbye, the Voyagers will continue their journeys in silence, deaf, blind, and mute, but still travelling at tens of thousands of miles per hour through the void. But their journeys are far from over, even if we can no longer hear from them. Voyager 1 is currently moving away from the solar system at about 3.5 astronomical units per year. 1 astronomical unit is the average distance between Earth and the Sun, about 93 million miles. Voyager 1 is heading toward the constellation Camelopardalis, though not toward any particular star in that constellation. In about 40,000 years, it will pass within 1.7 light-years of a little-known star in the constellation Ursa Minor, designated AC plus 79 38888. That's still a vast distance in cosmic terms. To put it in perspective, the closest star to our Sun, Proxima Centauri, is about 4.2 light-years away. So Voyager 1 won't be making a particularly close pass to this star, but it will be closer than it is to any other star right now. Voyager 2 is leaving the solar system at a speed of about 3.1 astronomical units per year. In approximately 40,000 years, it will pass within 1.7 light-years of a star named Ross 248, a small red dwarf in the constellation Andromeda. Currently, Voyager 1 is approximately 15.5 billion miles from Earth, while Voyager 2 is about 12.4 billion miles away. Those distances increase by hundreds of millions of miles every year, but here's something that might surprise you. Although both Voyagers crossed the heliopause years ago, they haven't technically left the solar system yet, at least not by one important definition. The Sun's gravitational influence extends far beyond the heliopause, much farther than most people realize. Scientists believe that the true edge of the solar system, defined by where the Sun's gravity ceases to be the dominant force, lies at the outer edge of the Oort cloud. The Oort cloud is a hypothetical spherical shell of icy objects surrounding the solar system at an enormous distance. It's thought to be the source of long-period comets, the ones that take hundreds or thousands of years to complete a single orbit around the Sun. The Oort cloud actually consists of two regions. The inner Oort cloud is disc-shaped and lies relatively close, perhaps 2,000 to 5,000 astronomical units from the Sun. The outer Oort cloud is spherical and extends much, much farther. Current estimates suggest that the outer edge of the Oort cloud lies somewhere between 50,000 and 100,000 astronomical units from the Sun. To put that in perspective, that's about 1 light-year, roughly a quarter of the distance to the nearest star. At their current speeds, Voyager 1 will take approximately 300 years just to reach the inner edge of the Oort cloud. It will then spend another 30,000 years crossing through it before finally, truly leaving the solar system behind. By that time, human civilization as we know it will likely have transformed beyond recognition, if it still exists at all. But there's another bubble surrounding our solar system that we need to talk about, one that makes the heliosphere look tiny by comparison. Recent research has revealed that our entire solar system exists within an enormous void in space called the local bubble. This discovery came from scientists at the Harvard-Smithsonian Center for Astrophysics, who used complex computer simulations to create a three-dimensional reconstruction of the space around us. What they found was remarkable. The Sun and Earth sit almost at the exact center of a spherical void, measuring about 1,000 light-years in diameter. This local bubble was created by a series of supernova explosions that occurred millions of years ago. About 14 million years ago, roughly 15 massive stars in our region of the galaxy reached the end of their lives and exploded as supernovae over a period of several million years. These catastrophic explosions pushed the interstellar gas outward with tremendous force, creating a bubble-like structure with a dense shell at the boundary and a relatively empty interior. The local bubble is still expanding today, though much more slowly than it did initially. When it first formed, it was growing at about 60 miles per second. Now it's expanding at about 4 miles per second, still a respectable speed on cosmic scales. What's truly fascinating is what scientists have found on the surface of this bubble. There are 7 star formation regions along the bubble's edge, dense molecular clouds where new stars are being born. This suggests that the compression of gas at the boundary of the bubble triggers the formation of new stars. It's a beautiful cosmic cycle. Dying stars explode, create bubbles in the interstellar medium, and those bubbles lead to the birth of new stars. The process of stellar birth and death shapes the structure of the entire galaxy. Here's another intriguing detail. Our Sun wasn't anywhere near the center of the local bubble when it formed. When those ancient supernovae exploded 14 million years ago, the Sun was about 1,000 light-years away from the action. But as the Sun orbits the center of the Milky Way galaxy, it slowly moved through space. and about 5 million years ago, purely by chance, it entered the local bubble and found itself almost exactly at the center. This timing is consistent with evidence found in Earth's crust. Geologists have discovered deposits of radioactive iron-60 isotopes in rocks dating back several million years. This isotope is produced by supernovae, and its presence on Earth suggests that our planet was showered with material from a supernova around that time, likely one of the explosions that created the local bubble. Scientists believe that the local bubble is just one of many such structures in the Milky Way. The galaxy is filled with these bubbles, created by generations of supernovae. The researchers compare the galaxy to Swiss cheese, with the holes punched out by dying stars. New stars form on the edges of these holes, and those stars eventually die and create new bubbles, in an endless cycle that has been going on for billions of years. The implications of the local bubble for life on Earth are significant. The lower density of matter in the bubble means we're less exposed to cosmic rays and interstellar radiation than we would be if we were in a denser region of the galaxy. Some scientists have speculated that being inside the local bubble might have played a role in the evolution of life on Earth, though this remains highly speculative. The structure of our cosmic neighborhood, then, looks like this. At the center is the Sun. Around it orbit the 8 planets, with Neptune marking the edge of the planetary system at about 30 astronomical units. Beyond Neptune lies the Kuiper Belt, a region of icy bodies extending to about 55 astronomical units. Then comes the heliopause at roughly 125 to 135 astronomical units, where the solar wind meets interstellar space. Far beyond that, the Oort cloud extends from perhaps 2,000 astronomical units out to 100,000 astronomical units or more. And all of this, the entire solar system including the distant Oort cloud, sits inside the local bubble, an almost incomprehensibly vast void 1,000 light-years across, itself just one small structure within the spiral arms of the Milky Way galaxy. The Voyagers have taught us something profound about our place in the universe. We live in a bubble within a bubble, protected from the harsh radiation of interstellar space by the heliosphere, and from the denser regions of the galaxy by the local bubble. These layers of protection have allowed life to flourish on Earth for billions of years. But the discoveries of the Voyagers extend beyond simple description of our cosmic neighborhood. They've revealed fundamental processes about how stars interact with the interstellar medium, how planetary systems form and evolve, and how the structure of galaxies is shaped by the life cycles of stars. The data they've sent back has rewritten textbooks and forced scientists to reconsider long-held theories. Looking back at the journey of these 2 small spacecrafts, it's hard not to feel a sense of awe at what they've accomplished. Built with 1970s technology, computers less powerful than a modern calculator, and power supplies that have been slowly dying for decades, the Voyagers have exceeded every expectation. They've visited worlds we'd never seen up close, discovered moons and rings we never knew existed, revealed the complexity of planetary atmospheres and magnetic fields, crossed into interstellar space, and sent back the first direct measurements of the environment between the stars. They've travelled farther and lasted longer than anyone dared hope when they launched nearly half a century ago. And they're still out there right now, at this very moment, hurtling through interstellar space at tens of thousands of miles per hour. Their weak radio signals are still being picked up by NASA's Deep Space Network, those giant radio antennas scattered around the globe that strain to hear the faint whispers from the edge of everything we know. The power levels of those signals are almost unimaginably tiny. By the time a signal from Voyager reaches Earth, its power has been reduced to roughly 1/10 of a billionth of a watt. Your digital watch operates at a power level 20 billion times stronger. Yet somehow, through the miracle of modern engineering, we can still hear them, still receive their data, still know that they're out there, carrying a piece of humanity into the unknown. The golden records aboard each Voyager represent perhaps the most poignant aspect of the mission. These phonograph records, plated in gold to protect them from erosion, contain a message from humanity to any extraterrestrial intelligence that might one day find them. The contents were carefully selected by a committee led by Carl Sagan to represent the diversity of life and culture on Earth. There are images showing the structure of DNA, mathematical definitions, the anatomy of humans, pictures of Earth and the solar system, and photographs depicting human activities and achievements. There are greetings spoken in 55 languages, from ancient Sumerian to modern Chinese. There's a 12-minute audio essay featuring the sounds of Earth, including volcanoes, earthquakes, thunder, wind, rain, surf, crickets, frogs, birds, whales, and human footsteps, heartbeats, and laughter. And there's music, 90 minutes of it, representing cultures from around the world and spanning thousands of years of human creativity, from Bach and Beethoven to Chuck Berry, and traditional songs from cultures across every continent. The records also include a message from President Jimmy Carter, who was in office when the Voyagers launched. His message reads in part, "This is a present from a small distant world, a token of our sounds, our science, our images, our music, our thoughts and our feelings. We are attempting to survive our time so we may live into yours." It's a message of hope, but also of vulnerability, an acknowledgement that humanity's future is uncertain, that we might not survive to see the distant future when these records might be found. Encoded on the records are also instructions for how to play them, written in what scientists hoped would be a universal language of mathematics and physics. A diagram shows how to use the included stylus to extract the audio and images from the grooves. A pulsar map indicates Earth's location relative to 14 pulsars, cosmic lighthouses that will continue to broadcast their precise signals for millions of years. The cover of the record includes a sample of ultra-pure uranium-238, which decays at a known rate, allowing any finder to determine how long ago the records were created. The likelihood of these golden records ever being found by an alien civilization is vanishingly small. Space is unimaginably vast, and the Voyagers are tiny needles in a cosmic haystack. They won't pass particularly close to any star for tens of thousands of years, and even then, close means distances of light years. The records are more likely to be destroyed by cosmic dust impacts or radiation damage long before they're ever discovered. But that's not really the point. The golden records were as much for us as for any hypothetical aliens. They represent humanity's hope that we're not alone, our desire to reach out and make contact with other minds in the universe, and our pride in what we've created and accomplished as a species. They're a statement that we were here, that we existed, that we dared to send a message to the stars, even though we might never know if anyone received it. The contrast between the golden records and the reality of the Voyager's current situation is stark. These spacecrafts were built to communicate with aliens, but soon they won't even be able to communicate with their creators. Within just a few years, both Voyagers will go silent, their nuclear batteries finally exhausted after nearly half a century of continuous operation. Mission controllers will have to make increasingly difficult decisions about which instruments to shut down first. Each shutdown will be like losing a sense, like watching someone you love slowly fade away. First to go will likely be the ultraviolet spectrometer, then the scan platform that aims the instruments, then the cosmic ray detector, and so on, until finally even the main radio transmitter falls silent. There will be one final transmission, a last digital goodbye, and then nothing. The engineers who have devoted years or even decades of their lives to these missions will watch their screens go dark for the last time. After that moment, the Voyagers will become ghost ships, sailing silently through the void with no one at the helm and no way to call home. But they'll continue their journeys nonetheless. They'll drift through interstellar space for millions, perhaps billions of years. They'll witness the slow dance of the stars, the birth and death of stellar systems, the evolution of the galaxy itself. They'll see things no human eyes will ever see, experience environments no human mind can fully imagine. And they'll carry those golden records, those messages from Earth, preserving a snapshot of humanity as it was in 1977. Long after everyone who worked on the Voyager missions has died, long after the cities they were built in have crumbled to dust, long after perhaps even human civilization itself has ended or transformed into something unrecognizable, the Voyagers will still be out there, still carrying their message to the stars. The scientific legacy of the Voyager missions is immeasurable. The data they collected fundamentally changed our understanding of the outer solar system. Before Voyager, we knew embarrassingly little about Jupiter, Saturn, Uranus, and Neptune. We could see them through telescopes, of course, but those views were limited by Earth's atmosphere and the vast distances involved. The Voyagers gave us our first detailed looks at these alien worlds, and what they showed us was beyond anything we'd imagined. The complexity of Jupiter's atmosphere, the intricate structure of Saturn's rings, the bizarre tilt of Uranus, the dynamic storms of Neptune, the volcanic activity on Io, the ice crust of Europa, the thick atmosphere of Titan, the geysers of Triton. Each of these discoveries opened new questions and new avenues of research that scientists are still exploring today. The Voyager data helped establish the field of comparative planetology, the study of how different planets form and evolve under different conditions. By comparing the gas giants and ice giants, scientists gained insights into the processes that shaped our solar system billions of years ago. The moons of the outer planets turned out to be worlds in their own right, each with its own unique geology and history. Europa's subsurface ocean, suggested by Voyager data and confirmed by later missions, has become one of the prime targets in the search for extraterrestrial life in our solar system. The discoveries about planetary magnetic fields, atmospheres, and ring systems have informed our understanding of exoplanets, the thousands of planets orbiting other stars that we've discovered in recent decades. But perhaps the most important contribution of the Voyager missions has been to change how we think about our place in the universe. The images they sent back, from the family portrait of the planets to the pale blue dot photograph of Earth, gave us a new perspective on our world and ourselves. They showed us that Earth is just one small world among many, that the solar system is far more diverse and complex than we ever imagined, and that the universe extends far beyond our tiny corner of space. These aren't just scientific insights, they're philosophical ones, with implications for how we understand our significance and our responsibilities. Carl Sagan, in his reflection on the pale blue dot image, wrote words that have become famous. "Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, Every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. His point was clear. Seen from a cosmic perspective, our differences seem petty, our conflicts absurd. We're all sharing this one small world, floating in the vastness of space, and we'd better take care of it because it's all we have. The Voyager missions also demonstrated what humanity can accomplish when we work together toward a common goal. The spacecraft were designed and built by thousands of engineers and scientists from around the world. The mission required international cooperation to track the spacecraft and receive their signals. The Deep Space Network facilities in California, Spain, and Australia worked in constant coordination to maintain contact with the Voyagers as Earth rotated. The scientific teams analysed data from instruments they designed and built, making discoveries that no individual could have made alone. It was a collective achievement, a testament to what humans can do when we pool our knowledge and resources. And the missions weren't without their challenges and setbacks. There were instrument failures, software glitches, and moments when it seemed like one or both spacecraft might be lost. The recent memory failure on Voyager 1 was just the latest in a long series of problems that the mission team has had to overcome. Each time the engineers found creative solutions, often having to improvise fixes for problems they'd never anticipated. They had to work with hardware and software designed decades ago, often by people who had long since retired or passed away, with incomplete documentation and no ability to physically access the spacecraft. It's a remarkable achievement of engineering and problem solving, and it speaks to the dedication and ingenuity of the people who've kept these missions running for so long. The Voyager missions have also inspired generations of scientists and engineers. Many people working in space exploration today cite the Voyager images as the reason they became interested in science. The photos of Jupiter's moons, Saturn's rings, and distant Neptune appeared in textbooks, magazines, and television programs around the world, capturing the imagination of millions. The missions showed that space exploration wasn't just about sending humans to the moon. It was about exploring the entire solar system and beyond, using robotic probes to go where humans couldn't yet go. They proved that unmanned missions could accomplish incredible scientific goals and that we could explore the solar system in ways that would be impossible with human crews. The technology developed for the Voyager missions has had lasting impacts as well. The spacecraft design, the communication systems, the power generation using radioisotope thermoelectric generators, the autonomous fault protection systems that allowed the spacecraft to handle problems on their own without waiting for instructions from Earth, all of these innovations have influenced later missions. The techniques developed to navigate the spacecraft through gravitational assists have been used by many subsequent probes. The Galileo mission to Jupiter, the Cassini mission to Saturn, the New Horizons mission to Pluto, and the Kuiper Belt, all of these benefited from lessons learned during the Voyager missions. Looking ahead, NASA and other space agencies are planning missions that will follow in Voyager's footsteps. There's talk of an interstellar probe mission that could be launched in the 2030s, designed from the start to study the heliosphere and interstellar space. This probe would travel much faster than the Voyagers, potentially reaching 10 times farther in a 50-year mission. It would carry modern instruments far more capable than those aboard Voyager, and it would be able to make detailed measurements of the regions the Voyagers are passing through with their aging, limited instruments. Some proposals even suggest using advanced propulsion technologies like solar sails or even nuclear pulse propulsion to accelerate the spacecraft to speeds the Voyagers could never achieve. Such a mission could potentially reach the inner edge of the Oort cloud within a human lifetime, something that would take the Voyagers 300 years. There are also ambitious concepts for true interstellar missions, spacecraft that could reach another star system within decades rather than millennia. The Breakthrough Starshot project, for example, proposes using powerful laser arrays to accelerate tiny spacecraft to a significant fraction of the speed of light, potentially reaching Alpha Centauri, our nearest stellar neighbour, in just 20 years. While such projects face enormous technical challenges and may not be feasible for decades, they represent humanity's continued desire to reach beyond our solar system and explore the galaxy. The Voyagers, in a sense, were the first baby steps in that direction, proving that we could build machines capable of functioning in interstellar space. But even as we plan for the future, we should take a moment to appreciate what the Voyagers have already accomplished. They've travelled farther than any other human-made objects. They've sent back data from regions of space no other spacecraft has visited. They've continued to function decades beyond their design lifetime. They've made discoveries that have rewritten our understanding of the solar system and interstellar space. And they've inspired millions of people around the world to look up at the stars and wonder what's out there. That's an incredible legacy for two machines that were built almost 50 years ago with computers less powerful than a modern smartwatch. The story of the Voyagers is also a story about time and perspective. The spacecraft have been travelling for nearly half a century, and they've barely begun their true journey through the galaxy. They won't leave the Oort cloud for 30,000 years. They won't reach another star for 40,000 years. And yet, from a galactic perspective, they're barely moving at all. At their current speeds, it would take them over 70,000 years to travel just 1 light year. The galaxy is 100,000 light years across. At Voyager speeds, crossing from one side of the galaxy to the other would take 7 billion years, roughly half the current age of the universe. Space is inconceivably vast, and even our fastest spacecraft are painfully slow on cosmic scales. This reality highlights one of the fundamental challenges of space exploration. If we ever want to truly explore the galaxy, to visit other star systems and search for life beyond Earth, we'll need to develop propulsion technologies far beyond anything we have today. Chemical rockets, which have powered every spacecraft we've ever built, including the Voyagers, are simply too slow. Even nuclear propulsion, which could potentially provide much higher speeds, would still require decades or centuries to reach even nearby stars. Some scientists speculate about exotic possibilities like antimatter drives or warp drives that could theoretically allow faster-than-light travel, but these remain firmly in the realm of science fiction for now. The laws of physics as we currently understand them suggest that faster-than-light travel may be impossible, meaning that interstellar journeys will always take a very, very long time. But the Voyagers have shown us that even with slow speeds and limited technology, we can still accomplish remarkable things. They've demonstrated that we can build machines capable of surviving for decades in the harsh environment of space, that we can communicate across billions of miles, that we can design missions that continue to produce valuable science long after their primary objectives are complete. These are lessons we'll need to remember as we plan future missions to explore the outer solar system and beyond. The key is redundancy, robust design, autonomous systems that can handle problems without waiting for instructions from Earth, and the flexibility to adapt to unexpected circumstances. The Voyagers had all of these qualities, which is why they've lasted so long and accomplished so much. As we approach the end of the Voyager missions, it's worth reflecting on what they mean for humanity's future in space. These spacecrafts were launched during the Cold War, at a time when the United States and the Soviet Union were locked in a tense competition that included a race to explore space. The Voyager missions were, in part, a demonstration of American technological prowess, a way to show the world what the United States could accomplish. but they were also something more than that. They represented humanity's curiosity, our desire to explore and understand the universe around us. The golden records carry messages not from America or any single nation, but from Earth, from humanity as a whole. They're a reminder that we're all inhabitants of the same small planet, sharing the same cosmic neighborhood. In the decades since the Voyagers launched, our world has changed in many ways. The Cold War ended. The Soviet Union collapsed. International cooperation in space exploration has become more common, with projects like the International Space Station bringing together astronauts and engineers from around the world. Private companies have entered the space business, developed new rockets and spacecraft, and pursued ambitious goals like colonizing Mars. Our technology has advanced dramatically, with computers millions of times more powerful than those aboard Voyager now fitting in our pockets. We've discovered thousands of planets orbiting other stars, found evidence of liquid water on Mars, and several moons in the outer solar system, and detected gravitational waves and black hole collisions that prove Einstein's theories about the nature of space and time. But in some ways, we haven't changed at all. We're still curious about what's out there in the universe. We're still driven to explore and discover. We're still capable of accomplishing great things when we work together. And we're still looking for answers to the same fundamental questions that motivated the Voyager missions in the first place. Are we alone in the universe? What is our place in the cosmos? Where did we come from, and where are we going? The Voyagers haven't answered these questions, but they've helped us understand them better. They've shown us how vast and complex the universe is, how much we still have to learn, and how far we still have to go. Soon, within just a few years, we'll lose contact with the Voyagers forever. That day will be sad for everyone who's worked on the missions and for everyone who's followed their journey over the decades. It will mark the end of an era, the closing of a chapter in the history of space exploration. But it won't be the end of the story. The Voyagers themselves will continue their journeys through the galaxy, silent witnesses to the unfolding cosmic drama. They'll drift through interstellar space for millions of years, perhaps billions, long after everyone who built them or followed their missions has been forgotten. They'll be humanity's emissaries to the stars, carrying our message to anyone who might find them in the distant future. And even after we lose contact with them, the legacy of what they accomplished will endure. The data they collected will continue to be analysed and reanalyzed for years to come, as scientists develop new theories and new ways of understanding the solar system and interstellar space. The images they captured will continue to inspire new generations to look up at the night sky and wonder what's out there. The technology they pioneered will continue to influence future missions, and the golden records they carry will continue to represent humanity's hope that we're not alone, our pride in what we've created, and our determination to reach beyond our small world and explore the cosmos. In that sense, the Voyager missions will never truly end. They'll continue to influence and inspire long after the spacecraft themselves have fallen silent. As we reflect on the Voyager missions and what they've taught us, we're reminded of a simple but profound truth. We are explorers. It's part of what makes us human. For thousands of years, we've pushed beyond the known boundaries, crossing oceans, climbing mountains, venturing into deserts and jungles and frozen wastelands. We've always wondered what lies beyond the horizon, and we've always been willing to take risks to find out. The Voyagers represent the continuation of that ancient tradition, carried forward into a new realm. There are ships sailing beyond the edge of the map, into the unknown waters of interstellar space. And just like the explorers of old, they've discovered that the universe is far stranger and more wonderful than we ever imagined. The Voyagers have shown us worlds where volcanoes spew sulfur into space, where moons are covered in cracked ice, hiding vast oceans beneath, where rings circle planets in patterns of astounding complexity, where geysers erupt from surfaces colder than anywhere on Earth, where storms rage for centuries in atmospheres of hydrogen and helium. They've shown us the boundary where our sun's influence ends and the galaxy begin, a place where two environments collide in ways we're still trying to understand. They've sent us messages from the void between stars, the eerie hum of plasma waves traveling through nearly empty space. They've given us a new understanding of our solar system, our galaxy, and our place within it all. But perhaps most importantly, they've shown us that we're capable of extraordinary things. We built two small machines in the 1970s with primitive computers and limited power supplies, launched them into space on rockets, and guided them across billions of miles to visit worlds we'd never seen before. We kept them running for nearly 50 years, far longer than anyone expected. We solved problems that seemed impossible, fixed malfunctions from billions of miles away, and extracted every bit of science we could from aging instruments. We sent a message to the stars, a greeting from one small species on one small world, just in case someone else is out there listening. That took vision, dedication, ingenuity, and hope. Those qualities are what make us human, and they're what will carry us forward into whatever future awaits us. As the Voyager missions draw to a close, as we prepare to say goodbye to these faithful servants that have travelled farther and lasted longer than anyone dared dream, we should remember what they represent. They're not just machines. They're monuments to human curiosity and ambition. They're proof that we can reach beyond our world and touch the stars, even if only with robots and radio signals for now. They're reminders that the universe is vast and full of wonders waiting to be discovered. And they're messengers carrying our hopes and dreams into the cosmic ocean, adrift on currents we're only beginning to understand. The Voyagers have been humanity's eyes and ears in the outer solar system and beyond for nearly half a century. Soon they'll fall silent, but they'll never truly be forgotten. They'll continue their lonely vigil through eternity, sailing forever between the stars, carrying the story of a small blue world and the curious creatures who built machines to explore the cosmos. That's not a bad legacy for two spacecraft that started their journey almost 50 years ago. And it's a fitting symbol of humanity's unending quest to understand the universe and our place within it.